Hello everyone, I am Babar and in this talk we will talk about the duality of subtyping, or in short, duotyping. Duality is an important concept in logic. In this work, we develop a novel technique which we call duotyping by employing the duality in subtyping relation. Instead of writing A is subtype of B or A is supertype of B, we write it A has some mode relation with B. The mode relation is represented with the help of diamond. This mode can either be subtype or the supertype. By applying duality in subtyping, it helps to simplify the subtyping design. It gives shorter specifications and implementation. It allows the discovery of interesting dual features for free. For example, when we apply duotyping in system F sub, it gives us lower bounded quantification as well as the upper bounded quantification. It also gives us the new proof techniques which are based upon the duality. So let's start with a traditional system. When we have a top type, a bottom type, integer type and the arrow type, we need 4 set of rules to form the subtyping for this system, that is ts top, ts bottom, ts int and ts arrow for the function types. What if we add more types in this system? When we add more types in this system, such as intersection types, we need more set of subtyping rules. Intersection types in this system are represented with blue, and when we added intersection types in this system, we need 4 set of basic rules, one for top, one for bottom, one for integer, one for arrow, and we need 3 more rules to deal with the intersection types. Now, what if we add more types or more features in this system? Let's add the union types. Union types are highlighted pink. When we add union types in this system, we need 4 basic set of rules, one for top, one for bottom, one for integer, one for functions. We need 3 rules for the intersection types, and we need 3 more rules for the union types. Since we are adding more types in the system, we need more subtyping rules. Now let's think for a moment, what if we add more types in the system? What if we add universal types? What if we add bounded quantification? Then we will need more subtyping rules. This implies that as we are adding more types or more features in our system, our specifications are growing, and larger specification is the one factor which contributes to the complex meta theory and implementation. Now a very basic research question here is, can we reduce the specifications or the number of subtyping rules while having the same features? So this goes to our first benefit of duotyping, that is shorter specifications with duotyping. If we carefully analyze this traditional subtyping system with top, bottom, integer, arrow, intersection and the union types, we see that in total we need 10 subtyping rules. And if we analyze this system more carefully, we see that ts top and ts bottom are the mirror images of one another, or they are the dual rules. ts top says that any type is the subtype of top, and ts bottom says that bottom is the subtype of any other type. Let's see if we can merge these 2 rules together into one rule by exploiting the duality. Since ts top and ts bottom are the dual rules, we can merge them together by exploiting the duality, and we can come up with gds top bottom as a one rule to accommodate both ts top and ts bottom. Now this diamond symbol is the mode relation, which can either be subtype or the supertype, and diamond with bars is a bound select function. that gives us either top or the bottom type depending upon the specific value of the mode. Now let's run examples and see if we can re-engineer the TS top and TS bottom from the GDS top bottom. When we have mode equals subtyping, by putting the specific value of mode and by applying the operation, we get that A is the subtype of top or any type is the subtype of top. And when we have mode equals supertype, we get any type is the supertype of bottom or bottom is the subtype of any other type. So these two results are equivalent to TS top and TS bottom, which means that we can generate two dual rules from one GDS top bottom. This technique could be further exploited on the more complex subtyping rules, such as the subtyping rules for the intersections and the unions. TS and A and TS or A are both the dual rules, and we can merge them together by exploiting the duality into GDS left. Again, we have another operation, that is choose type. It gives us either intersection type or the union type depending upon the specific value of the mode, and we can re-engineer TS and A and TS or A from the GDS left. Duotyping gives us shorter specifications of the compact specification. So this is a complete system, simply type lambda calculus with subtyping, intersection types and the union types. We have the unified subtyping rules for the dual rules, and the total rules are now 7. So this system is as powerful as we had the traditional subtyping system a few slides back. It has top type, it has bottom type, it has integer, it has functions, intersections and the union types. But the total subtyping rules are now 7 instead of 10 that we had in the traditional subtyping system. Another interesting thing to observe here is that the subtyping rule for the functions GDS arrow is not contravariant. Instead, we just flip the mode in the arguments. And we have a special rule here, GDS dual. So this duality rule or GDS dual, when we unfold GDS top bottom, it gives us two rules. That is, any type is a subtype of top and any type is a supertype of top. But here we are missing two rules. Our GDS top bottom does not capture two rules. That is, top is the supertype of any other type and bottom is the subtype of any other type. For the reflexivity, these rules are important to capture in the system. To capture such missing rules, we have a duality rule here, GDS dual. Duality rule simply inverts the mode and flips the arguments, and it captures the missing rules. Duotyping also allows us to discover new proof techniques which are based upon the duality. If we take the example of transitivity lemma, the transitivity lemma in a duotyping system is like this. A has mode relation with B and B has mode relation with C. This implies that A has the mode relation with C. This transitivity lemma can be easily proved by induction on the duotyping relation, while induction on the subtyping relation is not possible in the traditional subtyping system because of the contravariance issue. Also, this transitivity lemma can be further divided into two transitivity lemmas, that is one for subtyping and another one for supertyping, because this mode could either be subtype or the supertype. Duotyping also gives us some interesting extra features for free. When we apply this duotyping in a polymorphic system, we get lower bounded quantification as well as the upper bounded quantification. F sub, the traditional F sub only has the upper bounded quantification, while F sub with duotyping gives us both upper bounded quantification as well as lower bounded quantification, and this comes for free in duotyping. If we see the GS for all KFS here, we see that this type variable X has a mode relation with A. So this is not specific to just subtyping. This mode could either be subtyping or the supertyping. Nerving lemma is also interesting in the duotyping system. The traditional nerving lemma captures just a subtyping relation, while the nerving lemma in duotyping system captures both subtyping and the supertyping relation. And the proof complexity is almost similar of both the transitivity lemmas in the traditional system as well as in the duotype system. Now, since we saw introduction of the duotyping, a question here is, why should someone use duotyping? Or does duotyping offer some benefits that are not available in the traditional subtyping systems? To answer this question, we compared some traditional subtyping systems with our duotyping systems, and we followed an empirical approach in our comparison. To be specific, we compared the number of subtyping and the duotyping rules in both the systems. We compared the lines of code required for the transitivity lemma proof, and we compared total lines of code required to prove the meta theory in ECOOP. In our first comparison, that is between the number of subtyping rules in a traditional subtyping system and the duotyping system, the first two columns are related to the traditional subtyping systems. First column shows traditional system, while the second column shows the number of subtyping rule in that specific traditional subtyping system. Third and fourth column are related to the duotyping system. Third column shows the duotyping system, while the fourth column shows the respective number of duotyping rules in that system. While the last column shows the extra features that are provided by the duotyping system, which are not provided by default by the standard subtyping systems. Number of subtyping rules required for simply type lambda calculus with subtyping in traditional approach are 3, while the number of duotyping rules in simply type lambda calculus with duotyping are 4. This is because duotyping also offers an extra feature of lower bounds. If we add lower bounds in simply type lambda calculus with subtyping, we need one extra rule, which will be 4 in total. Similarly, as we move from the simpler systems to the complex system, we see that as we have more dual features in a system, duotyping captures those dual features into unified features, and we get the less number of rules in the duotyping systems. So in general, duotyping rules count is less than the traditional subtyping counts, and duotyping also provides extra features of lower bounds and the lower bounded quantification. Our second comparison is of the transitivity lemma, because transitivity lemma is usually the hardest to prove for the subtyping. The first column shows the traditional subtyping system, while the second column shows the respective lines of code required to prove the traditional lemma in the traditional system. Third and fourth column are related to the duotyping system. Third column shows the duotyping system, while the fourth column shows the respective lines of code to prove the transitivity lemma in that duotype system. We need 7 lines of code to prove the transitivity lemma in simply type lambda calculus with subtyping, while we need just 4 lines of code to prove the transitivity lemma in simply type lambda calculus with duotyping. As we move from a simpler system to a complex system, we can see the significant drop in lines of code for the duotyping systems. For example, we need 38 lines of code to prove the transitivity lemma in system F sub kernel with intersection types and the union types in a traditional approach, while we need just 18 lines of code to prove the transitivity lemma in F sub kernel with duotyping, intersection types and the union types. In general, Lines of code for duotyping transitivity proof are less than subtyping transitivity proof. And we also do not need double induction in function case to prove the transitivity, because as we saw, the subtyping rule for functions is not contravariant. So in summary, we develop a novel technique, duotyping, in which we employed duality in subtyping relation. And we examined several type systems with duotyping, from simply type lambda calculus to F subkernel with intersection and the union types, and we show that this duotyping is a practically applicable technique. We proved duotyping flexibility, symmetry, and the transitivity, and we have meta theory formalized in the Koch theorem prover. The code is available for your reference at the given link. Thank you for your attention.